Okay, let's get started. So today we have quite a bit to talk about. I'm going to finish the ADMM today. I think I have a few slides left. Then after I finish, this will probably take like 15 minutes to have it done. Then we're going to talk about the final group project. That hopefully we can finish that in about like 10 to 15 minutes. And after that, we're going to continue to about the penalized methods. Okay, so that's a agenda for today. So as I explained, the ADMM it can help within the parallelized computation. Even when you have this is your function is not separable, right? When you have target function f is not separable. Now it's based on two results. One is we assume, so for the ADMM itself, okay, ADMM itself is based on for the dual ascent method, but this dual ascent is the result just generalized from the one step from the usual dual ascent methods. Because for the usual dual ascent method, we have a target function f, and this f is not separable. So it has the equality constraint. We can use dual ascent to maximize this. The result is good. Now, for the ADMM, it just push you one step further, saying suppose my target function is separable with two sets of parameters, okay, x and z, and then the subject to linear constraint on the x and z. Now, this is basically the ADMM result saying the dual ascent the method still works, okay, by iteratively update x, which is one set of parameter, and the z is another set of parameter, and y, which is the Lagrange multiplier. So by iteratively update, this is x, z, y. Iteratively, you still can converge, or they can still get reach the minimum optimum point. Now, using this ADMM methods, we can just say we can separate them into two sets of parameters. But this is not the real parallelization come from, right? Because I said this is we just can say this will hold for if your parameter space can be separated into two sections. Now the parallelization comes in when we assume using so-called the consensus optimization. In this optimization, we can write our problem, okay, which is minimize the summation of the negative log likelihood function for each part of data, right? Then we assume each part of data, each segment data has its own parameter xi. However, we constrain them. Okay, we constrain them. We subject to a constraint. Say each parameter for the segment data, it has to be equal to a consensus parameter z. So then in this case, we kind of like artificially, okay, we introduce a new set of variable called z. Z is a consensus parameter. Then with that, we kind of like making the target function separable into two sets of parameter by this artificial including this is another set of z. Now with this, we can parallelize the computation or the optimization for the xi, right? Which is parameter for each segment data. So with this so-called consensus optimization, we converted our problem, okay, by instead of optimize this is a parameter on all the data set, on the whole data set. But now we convert it into the problem like we can, because essentially if you want to minimize or optimize the overall function in the ADMM form, we can just minimize the fi xi by itself, right? Because the parameter separable. So each segment data, they're independent from each other. So therefore, you don't need to have a global optimization. Instead, you can work within the optimization on each segment data. Now, once you have the segment data, what you try to do, you have to constrain them to be the same set of sort of consensus parameters. So that's a whole idea behind using from ADMM to the consensus optimization. So with that, we can sort of like writing our augmented the Lagrangian within the ADMM. It writing in the above, right? So now another thing I think is a little bit need to pay attention is now your Lagrangian multiplier y is yi is specified. So it's specified specific for each segment data, because then your constraint is for each of xi, right? Xi minus zi. So each segment data will have its own constraint. So therefore, your Lagrangian parameter y it has a subscript I here. Z is essentially your Z is your the sort of like the so-called consensus is your ultimate target. That's because when every xi reaches to a consensus, then the Z is your global optimal point. So this is ADMM again. It just it's iteratively now. It still has in the iteratively update the parameter, like you can update the x first and update the z and update the y. However, for the x updating, right, you can see because the x they are now I've broken them into like each of xi, x1 up to xn. So therefore, you can actually parallelize this is the x updating, which is by using this form. Now, I think I jumped from this slide right to the logistic regression the directly. Now we have a few results has been derived here, right? One is if you remember, we have the summation I of yi. This is equal to 0. Remember, we kind of derived this, right? So if this is equal to 0, right? Let's just lay out some result here. Remember, if you divide this is if you divide this is a yi by rho, we can write this thing as a mu, right? As another parameter mu. So therefore, summation of I of ui, this is also equal to 0. Ui essentially is equal to yi divided by rho, right? By the parameter rho. So let's set the results by the side. With this result, right? With this result, now the algorithm above can simply be simplified to the following. Okay, by the simplification would be when you update this is when you at for each per segment data, what you try to do is try to minimize the fi(xi). Fi(xi), this is the negative log likelihood function for the data, right? So this is a negative log likelihood. So you want to minimize the negative log likelihood. Plus, you have this is yi, k, this is the yk is the Lagrangian multiplier you're getting from the previous step, right? So this is updating. So you have yi, k from the previous step. Now you have xi minus x bar k. This is from before. This is you want to have xi minus zk, right? Because of this is a yi summation I of yi equal to 0. So you can see from this step, your zk is your zk plus 1 is actually equal to what? So your zk plus 1 is actually equal to your updating for the zk plus 1 is actually just equal to x bar, right? It's just equal to x bar k plus 1. So well, in this case, that's bar k because it's from the previous step. Is it from the So you can see here you have in when you try to update in your xi, your z, which is x bar k, is from the previous step. Your yi is from the previous step. It's just only thing you want to do is now is minimize regarding xi, right? Then your method multiplier, the quadratic term is xi minus x bar k. This is L2 square of L2 norm. Is in the last term. Then when you update the yi, you essentially what you just do is just replace this you just replace z with x bar, right? So what we did here is we just skip the z, right? We just include the z by replacing z with x k bar in there. Essentially, this is just basically this now is just basic two-step. Okay, we don't have this is a consensus. We don't need to work with the consensus the parameter explicitly, but it's embedded in there, right? It's embedded because z is equal to x bar. So now within this formula, what you can see is in each iteration, what we're going to see, we're going to gather the xi and the average to get x bar k, right? So think about it. Now you have you have a master node here, right? You have a worker node, 1, 2, 3, up to like n. So you have this is a master node and a worker node. They can coordinate each other to making this work. Then so the algorithm basic works is you have a initialization, right? You initialize for each of this is the xi. Now when you have in this is a so what you can do basically another thing you can do is you can just by regression or the feeding the data locally, right? Locally for each processor. Then you can have in so like you have your x1 1, right? x2 1, right? So you can have this is a your estimation, local estimation, right? You have a local estimation for each segment data. Once you have a local estimation for each segment data, what you can do, then you can just send it to the, because now remember the worker they don't talk each other, right? What you can actually do you can actually make them talk each other by in this design we're using this is a sort of like master worker this is structure, but in your projects you can actually just do like a scatter or and gather all. Right? You can just have everybody has its xi. You can just scatter it to everybody. Okay. In that cases you can you still need someone to coordinate. It's better to just using this is having a particular like a root node or like a master node to control for the central update. So in that case, say everybody update you have your local calculation, then everybody can send it to master node. Master node is just do a simple calculation, right? Just keep calculating the x1 bar, which is just simply averaging out. Once you have this average, then this master node is going to send it back. Okay, this is basically scatter, right? Scatter to the worker, and then send it back to the x bar 1. Once each worker received x bar 1, what you can do is can using from x bar 1, they can get in this is a y bar. They can update the yi1, right? So they can update this y1 1. They can update their multiplier. Once they have their the multiplier Lagrange multiplier being updated, right? So you once you have this updated, so you can send they can do the local optimization, okay? Local optimization, which is you have this yi is given, this x bar is given, then the only thing is don't know is xi. Then you update your locally xi locally, then send it to calculate the x bar, and then the x bar is scattered to get in update locally, so update yi and update xi corresponding. Okay, so this is how the consensus optimization with ADMM works. With this we can say then we can basically is realizing the parallelization on all segment data. Okay, they are actually pretty good statistical property with this. Okay, now if we look at this, okay, this is the Fi. Okay, what is Fi? Fi is the negative log likelihood, right? Because we want to maximize the log likelihood, but then if you want to convert it to like minimization, so then the Fi is a negative log likelihood. So if you look at the last two terms, right? The last two terms, as we see now, you have a quadratic term, you have a linear term. These two terms, okay, can actually be converged, okay, can be putting together. This actually can be written as something like this. Rho over 2 times this is the xi, okay, minus x bar k, plus 1 over rho times this is yi. Each of them, notice here, each one of them is a vector, okay? Is a vector. This can be writing as a transpose of xi minus x bar plus 1 over rho of yik, okay? We have shown this is what we have talked about this before, right? When we talk about ADMM, we say the last two terms, the quadratic term, these two terms actually can be merged into one term, right? Plus some constant term, plus some constant. This constant does not contain any xi, right? So the constant which is does not contributing to minimization, okay? This term right here, if you are familiar with in the if you're familiar with in this is the normal distribution a little bit. This is the kernel of the multivariate normal. Okay, this is a kernel multivariate normal. Remember here, this f is a negative. Okay, is a negative log. This is a negative log likelihood, right? Is negative log likelihood. Now plus this is some part here. So if you taking the exponential on both sides, okay, if you're taking the exponential on both sides, on the whole thing, on the whole function, what you have is you're going to have your likelihood function multiply e to the power of this guy, right? Because if you this is what you're saying here, the target function over here is on log scale, right? It's on log scale. So if you convert it back to the on the likelihood scale, on the likelihood. So then what you try to do is minimize your likelihood function multiply e to the power of this quadratic term, right? This quadratic term right here is the kernel of the multivariate normal, okay? Because this is just by you putting a normalizing constant here, this has become the multivariate normal density function, okay? Multivariate normal density function. So what basically this saying is, okay, what basically this saying is, your xi k plus 1 basically is a MAP estimation under the prior of this multivariate normal, okay? Oh, that's actually a typo here. This should be minus, okay, instead of this should be xk minus 1 over yk. Why is that? The MAP is basically maximum posterior, right? Maximum posterior. So what basically this is saying is if you know a little bit about Bayesian statistics, okay, if you know a little bit of Bayesian statistics, the function given in this is updated for xi. This is basically your the distribution for the data. And then this is a distribution for your, this is the distribution for the xi, right? This is a distribution for your prior, for the parameter. So then these two multiplied together, this is will be their joint distribution, right? Joint distribution of your data and the parameter, okay? Data and parameter. So which is proportional to the posterior distribution, okay? When if you don't know about this, then that's fine. We can just because really this is a like I said, this is I designed this class originally is mainly for people, for students in the statistical track, but I understand this is a data, most of the class right now is data science. So if you guys are not really familiar with the Bayesian statistics, or you are not familiar with this is so-called MAP. MAP, this is MAP stand for maximum. This is for maximum posterior, okay? Posterior. That's basically saying this is estimation. You want to maximize the posterior distribution, okay? Maximize posterior distribution, and you get in for the xi. So if you are not familiar with Bayesian, not familiar with this is the MAP, that's fine. Just take this as given, okay? Because it's given. Now the prior mean, so this is the prior distribution, right? This is a prior distribution. So basically we assume xi follow this guy. So we have our data, okay? I have a data I. What is just saying is what I just saying here is we have data I. We have data I is follow a distribution with fi, right? Of x given, well, fi was, let's say, di given xi, okay? So this is the distribution for my data, okay? Data I, let's say, is di. Now, then the prior basic thing, I assume my xi is follow, this is a multivariate normal, right? This is our prior distribution. So then the posterior distribution of the data I, which is posterior distribution, which is xi given the data, this is going to follow, basically it's going to proportional, okay? It's going to proportional to be, this is fi times, this is the, let's say this is for the g of xi, right? This is a distribution for the g of, oh, actually it's better using normal, right? Normal xi. So this would be the posterior distribution. Is proportional to the original density of data times the prior, okay? And then using some normalizing constant, we usually, this is normalizing constant, we can ignore it. We can just working with it. So therefore, when we working with the posterior, is you just multiply this fi times this is the normal density. So prior mean, okay, if you look at the prior distribution, the prior mean of the xi essentially is the the consensus from the previous iteration, which is x bar, right? X bar k. So it's a consensus from the previous the iteration, shifted by so-called the price of the process I disagree with the previous consensus. Okay, this price is shifting by is this yi, okay, yik. So this is therefore this prior mean, the mean of the prior distribution is not like random, okay? It's coming from the consensus from previous iteration shifted by some value, and this value would be the when the process I disagree with the previous consensus, because when you having this is they are become more and more agree to each other. This is so-called shift. It will become smaller and smaller as well. So therefore, for each processor, okay, for each processor, which is only process data segment I, so you only need to support a Gaussian MAP method, okay, Gaussian MAP, which can be done using the you can either do it using the gradient methods or some other numerical method, okay. So but the thing is the data is small, okay. It can be handled within each processor. So this should be pretty simple. So on type of number data in block is round-robin, and the consensus protocol yield global maximum likelihood estimation. So actually MAP here is maximum posterior probability estimation. Actually, I read it here. Okay, so this is just to sort of like wrap up for the from the previous the class. One is I want to show you, this is when the main is about this statistical property. Okay, you need to understand it. It's sort of like the statistical is not a random, it's not a random thing. It actually has a good property for us to work with. So any question on this? Any? Okay, I do understand is, man, not everybody is familiar with the Bayesian statistics and also with MAP. So you, like I said, if you don't know what I'm talking about, okay, just take it as a given, okay. But if you do know a little bit statistics Bayesian, you can derive this as try to derive this as by yourself to see this makes sense to you, okay. It actually, to me, I think this is a pretty elegant result. Now, for the ADMM update, for the if we apply it to the if we apply this to the logistic regression, right? Basically, what it does is we have a data. We can partition them into key the segments. Now, for each segment, we can run the logistic regression. then this will be a local update. And then once you have logistic, then for run each logistic regression, so you're having sets of the parameter beta for each set part of data. Then you can calculate consensus and then go back and forth, right? Just like we did it we did it before. Now the consensus, as I mentioned in last class, the only thing you need to figure out, okay, which is the local updating. This local updating involving that's a so-called MAP estimation, right? But we don't need to really need to know Bayesian to optimize, so like minimize this function, or you just treating this as a beta I as your parameter, okay? Beta I as a parameter. You can just apply your usual the gradient methods, okay? Gradient method to do that, because we have seen before. Let me just writing a little bit more. So we know the Li, this is the log likelihood of the logistic regression, right? It's a logistic regression if you get it from the previous step, so you can you know what's formula look like. So DLI respect d beta I, okay? DLI equal to d beta I. What is this? This essentially is equal to this is essentially, well, let me okay, let me just write here. So this essentially is equal to the xi transpose. Remember, I hope you still remember, yi minus mu I. Okay. I here, remember, I here, this is so second data, okay? Second data. So this is mu I. They are all vectorized, right? The xi is your matrix, yi is a vector for the whole data, mu I is a mean for the whole data. Then you're having the derivative of the second term, okay? Derivative of second term. This guy derivative of d beta, because it's so hard to write in the mouse, okay? So I just want to give the idea. So this is going to be equal to rho times beta I minus beta k plus this is a ui. Okay, this is uik. This is ui and the mu I, they're different, right? This is mu I. Well, let's just do pi I. Okay, this will be easy. Pi I would be the parameter for the logistic regression. This is ui here. This is for the Lagrangian multiplier from the Lagrangian. So you can see basically for this whole function, okay, its first derivative is given, right? The first derivative can be calculated. Now with this being in mind, you can also calculate in the second order derivative. Okay, let's call this whole function in here is function. This function, like say, is function g. Then dg. The second order derivative of the function g of d beta I, right? Well, actually d beta I, because the beta I is a vector, so actually is d beta I transpose d beta I, right? So this is going to be equal to xi transpose. Remember, this is going to be di dt times xi, okay? And then plus the second term here, if you take in the derivative of beta I, this is just rho. You can see for the first, this is optimization, okay? Optimization. If you don't have the so if you don't call any existing method, you can derive the first order and the second order derivative with respect to beta I by itself with this formula, right? Which is given. So now the Newton, you can use basically the Newton's method to updating. Okay, so so the beta I optimization is actually not should not be too difficult, right? Now once you have in the beta I updated, now next step is update the yi, right? Yi we just now I'm writing as a u, but remember what is ui? Ui is equal to yi divided by rho, right? So this updating essentially is the same as updating your Lagrangian multiplier. This is the same. The only thing now I'm writing them as u instead of y, but they are almost interchangeable, right? So this is So any question regarding to this updating? So this is now in here we combine the logistic regression and the ADMM together. Okay, so this is this slide actually contains quite a bit of information. In order to understand here, you need to be familiar with the ADMM, and you also need to be familiar with the logistic regression, right? Likely function. Okay, so this is I mean, if you can understand this class, like the two equation on this slide as well, I think you are in a really good shape. Okay, that means you kind of understanding like in previous like probably like the 4 to 5 classes you did it pretty well. Okay. Any questions before I move on? Okay. Now, usually quiet response, quiet class usually doesn't mean everybody really understand it. I think it's I can sense some confusion, okay, right now. But if you do let us know, okay, let me know and let TA know so we can help you sort it out. But this is I think this is really important for you to get into the details for the for this two line. So this is if you apply this is this is some real data. This is KDD COB 2020 data. The data it contains is a binary response, has about 20 million covariates. That means your y the x the feature dimension is 20 million. Okay. Now if you only keep the covariates with more than 10 occurrence, it can reduce to like a 2.2 million covariates. But still 2.2 million the columns is still a lot of, it's a very large number, right? The training sample contains about 8 million, 8.4 million samples. The test data contains about 500,000 data. Okay, you can see this is data basically is 8 million by 2 million matrix, right? It's a huge matrix. Okay, the usual logistic regression is simply not going to work. Even your test data have like a 500,000 sample. This is still quite a bit. Then if you're using the logistic regression, we just discussed it previously. We can do like a 300 iteration, 600 iteration, or partition, 900, like 1200, right? You can, because the more you partition data, you have more parallelization, but you need more source, right? Resources for the computation. You can see basically if you do less partition, that is the smallest one is one partition, right? One partition will be just one global maximization. You can see when you do more partition, actually the log likelihood, okay, it all goes up, but it's still there's a small gap, okay. Basically, what this means, if you have smaller number partition, okay, the smaller partition you have, like it converge faster, okay, converge faster. But if you even taking like 1,200 partition, you can see that when they getting up to like 80 iterations, the distance between it's actually become quite small. Okay, it's not that big because they go up actually pretty quickly. That means, but large partition can make your program run faster, right? You take most of it go. This is basically what this slide just basically tells you is by partitioning your data with large partition, you didn't lose that much. Okay, lose a little bit. Okay, you do lose a little bit on the log likelihood, but you didn't lose so much. You can make up this difference by run more iterations. Okay, by run more iterations. This is on the task AUC versus number iteration. The task AUC, this is where AUC is a measurement to, this is called error under the curve, right? This is a measurement the accuracy for the algorithm. Again, if you are not familiar with AUC, then just taking this given as just as a measurement of accuracy, okay, for the algorithm. Because the task AUC actually is kind of reached to the top at the iteration 4 and 5. And when you have in the large partition, its AUC actually indeed is smaller. Okay, is smaller than the 300. But you can see the accuracy level is already, because the reason is looks this looks big because now you can see on the y-axis, I'm zooming in, right? You see the details. But if you look at the real percentage, okay, percentage or the value is like 0.4 versus 0.3. It's actually in a pretty small distance, okay? If you can zoom out, actually they can become almost at the same point. So this is also saying to show you that is with 300 under the 1200 partition, they have some small difference. Okay, they don't get me wrong. You can lose some accuracy, but that accuracy is if the accuracy is between the something you can have the job done versus you cannot have the job done, that sacrifice is worthwhile, right? That sacrifice is worthwhile because then if you cannot parallelize them, you cannot get any information at all, right? So, but when you in practice, when you do that, you should using like the smaller partition, the better, okay? The smaller partition better. So you have to try it out to making the partition to such that is a smaller enough, but you can still be able to handle them. Now, some other is a better convergence can be achieved by better initialization. You can use the result from naive method to initiate the parameter, right? Like I mentioned here, for the initial cycle, you can just simply run your logistic regression locally, okay, without even consider about consensus or the global machine. You can just run your logistic regression locally, just like call a logistic or whatever algorithm you can have, get them locally. That local estimation would be better than a random guess, right? Because that estimation, although it's not a global optimization, it's local, but that local is generated from data, okay? So if your data is representative, the whole data is homogeneous, then that estimation, the first run is still is better than the random guess. So therefore, should be able to converge faster. So you can also adaptively change the step size rho for each iteration based on the convergence state of the consensus. You can in your project, okay, rho is something you have to try it out. You can see what number of rho you can keep it. For the project, I think you can just keep the rho to be constant. But in practice, people usually multiply the rho by some multiplier. Okay, using updated rho is equal to the rho is equal to rho times epsilon, and this epsilon is bigger than 1. Okay, making the rho like these steps become a little bit larger. By doing that, okay, what you can see is when you have a larger rho, remember you can have if you come back to here, by doing the larger rho, what essentially by doing larger, what essentially is by making this is a shifting, okay, by making this a shifting, by giving the shifting from prior mean becomes smaller, so because this is 1 over rho, okay, so that means you're away from your the consensus will be smaller and smaller, so which you can reach into the convergence. More notes here. This is ADM around 1970s. ADM gave the single person algorithm that can be compatible with CDR, can be called in many. So these are things we already talked about. Okay. So these are the main thing about there's a little bit left over from the last class about ADMM. So I want to just finish up. So one is go through the statistical property of the algorithm. The second is show you like in a real setting. Okay, and this is the data can actually it can actually work. All right. So any questions on the ADMM before we move on? Okay. All right. So if you don't have any question now, then so the next item on the agenda is talk about final group projects. Okay, is now here is first thing is we have so that with the help of TA the whole class in both sessions, in-person session and the online session, okay, has been separated into 10 groups. Okay, so basically we have 69 students for the in-person class. So therefore we separate the in-person class into 7 groups. So one group will have 9 people, another rest will have 10 people. For the online session, I have 25 students. Then this is 25 students, we separate into 25 3 groups. So therefore, well, this is going to be 8, 9, okay, 8 and 9. This is, I don't want to, basically, they all just want to keep them separate because in-person class is going to present, make a presentation in person. Online session, you're going to make a presentation online through Zoom. But I do want to making this everybody to essentially this is one class, okay? Just have in person and online. But the reason is we cannot host everybody in the classroom, okay? This is so that's why we still keep this setting. Now we can come back to see the assignment just in later, okay? So basically we have 10 groups. Now, I also gave a few suggest topic for the final projects. Okay, the topics for final project should be something related to large data or big data analysis. Okay, but those topics not covered in the class. So therefore, I have this topic being listing here. This is like I have 2 groups of topics as well. One is finding similar items, large scale link analysis, large scale frequent item set, clustering, advertising on the web, the recommendation system, mining the social network. This is a dimension reduction, neural net and deep learning, online learning. I don't think I have time to go through online, but I want to list here as one project suggested. Then also the Spark and PySpark, I didn't really talk about it. If anybody interested, we can. This is another way like speed up the Hadoop. Okay, this is so for this one, if I have this chapter being labeled here, then this will be coming from this book, Mining of the Massive Datasets. They actually have the online data, online version of the textbook being free available, so you can check this. You can also, okay, in addition to this topic, you can also, if you like discuss with your group member, you can also suggest your own topic. Right? This own topic is called like more. It's more related to the big data, but still it's going to be related. No, it's still going to be related to big data, but it can be on some other topic. Like if you have one data that you have done before, and then you guys want to explore that, that's also fine. And there are more potential the topics which is not really analysis, but is also making related big data is big data security and privacy, big data for healthcare, financial transaction, fraud detection, climate change, and retail inventory management. This data set, which is like you see, if you are interested in any of this, you can present them as well, okay, and more. But this you need to find your own data. Okay, you need to find your own data, and then to find your own resources. So to work on them. So one. So in project 3, do we need to use L2 recognition? Oh, this is actually from the. I'm talking about final project. This is not the first of all. This is what I'm talking about. This is not project 3. This is your final group project. Okay. Your project 3. You do need to some L2 regularization because that's what we talk about like in the slides. You different from the regular logistic regression is by the L2 term, right? Norm in the behind. So right now I'm starting because your project 3 you haven't submitted yet, right? But I do want to start early to give you guys about the final project because then you can start you still need time to group together because this is a group you have to first have have everybody meet together, choose a topic. You need some time to decide, make a decision. Okay, so so I want to, even if you haven't finished project 3, I want to give you this topic so you can start thinking early. Okay, start thinking early. Now, once you have checking this exam, the topics, okay, Then for each group, you can email your top 5 choices, okay? Top 5 choices ranked in the order preference to TA, to our TA. And then the assignment topics, if you choose it from above, okay? If you can propose, if you propose your own, there's no competition, okay? Just propose your topic, that's fine. But if you're choosing from this list topic, okay, then this topic assignment will be like on a first come first serve basis. That means whoever email the TA first, you get a topic. That's why you need to email her top 5 choices, because if your first choice is taken by others, we're gonna go to the second one, and then next, right? But you will receive the confirmation email from us to see which topic is your chosen topic, select topic, okay? At the end, each group will give a final presentation on your selected topic. Okay, this is and the project slides are due on November 30th at 5 p.m. That means the December 1st, we are using December 1st and December 3rd as our presentation. Then November 30th is a Sunday, okay? So you need to, for both group, okay? No matter you present it on the Monday or Wednesday, you need to send the presentation slides by the November 30th, at the Sunday, 5 p.m. Now there's a trick, right? There's also a twist here, because that weekend is Thanksgiving weekend, okay? So November, I believe November 26th is what the 7th. That's a Thanksgiving. So likely, I would strongly suggest you guys, if you can finish this a little bit early, instead of like waiting for the, instead of like spending like the holiday to work on this. It's a good idea to probably on finish early. But I do want you, in case some group, if you want to like work, you cannot finish, but you still have some extra time on the weekend, okay, to finish up. The presentation should including this is at least this is a four the 4 parts you should have in the introduction and motivation. Say for example, you're choosing a large scale clustering, right? So you need to giving the some introduction and motivation for the problem, okay? Then you can dive into the method. Method could be the method is like a general method for the small data set, like say they're doing clustering, right? So the clustering can working for like reasonable small data set. But then you need to see, once you have introduced a general method, but then you can see how the method can be adapted with big data, okay? So then that's the you can use in this so the method in here is including both. You can talk about both is a small data method and also the how do you apply that method into big data. I mean, for the for what we're gonna actually we can cover this as well, like logistic regression. I first discussed how the logistic regression is done, like in general how it's done, and then how to extend it to the big data, right? Now then, next one I want you guys to talk about an example which is on a similar data. It could be the example could be if you can find a real data set, that'll be good. Okay, but if you cannot find real data, you can, if you similar data set, that's also fine. Okay, but the point is to using a data to example to demonstrate the methods. And then we also want you include the implementation with MPI for Pi. So this is the implementation. Basically, is you need to have some kind of script. Okay, you can have a Python script, which can be submitted. You can either include in your slides as so like the more slides, or you can include as a separate script file. Okay, then at the end of the class, I will distribute everything to the class. So if, say, for example, if you work on advertisement on the web, and then in the future, somebody, if you just in case, right, you step into that field, you have some things to start with. Now, for the presentation, since each group we have at least 8 people, 8, 9, 10. It will be so we have each class we have like 80 minutes, right? And then we're gonna have 5 presentations for each class, which means that means each presentation roughly gonna last about like 16 minutes. Okay, 5. So what I want to do here is it's probably not feasible for everybody to speak But you guys decide, okay? You guys decide within the group who want to present. It doesn't matter, right? It's at least you should have like 4 people to present, okay? Like you can just using the best 4 people you think in your group. But that the presentation needs to be clear, okay? Needs to be understandable, which means I have a very simple rule to decide how is a good presentation or not, okay? Which is all the people hear presentation, okay? Do they have a take-home message? All right. So if people are sitting down after hear presentation, they learn 1 point, okay? They learn something or like 1 point. They have 1 take-home message. I think that's a good presentation because you only have like 15, 60 minutes to cover method. I mean, I don't expect you everybody have you cover every single detail, right? This is not feasible. But you should make your presentation as clear as possible, like motivate people like when this message should be applied and how this message should be applied, and you should have 1 take-home message. And if you want to summarize, this I will ask you at the end of the presentation, okay? This is I want to ask each one of you, okay? Is to if you summarize, if you can summarize your presentation into 1 sentence, what it would be. So you better when you prepare your presentation, you should think of that question, okay? If you want to have in 1 sentence to summarize your presentation, okay, that's a take-home message for everybody and what it would be. So, but the presentation, the slides will be available to the class at the end. So even you cannot like catch all the details, right? In the future, if you are interested in some topic, you can go back to dive in. Okay, so that's the idea. Now let's see the group assignment. Okay. What I want to do here right now is I want to for each group, I want to have a group contact. Okay, have a group contact. Basically is to this because now probably not everybody knows everybody. Okay, which means this group assignment is random assignment. So the first thing you guys need to do is to have your group meeting. Okay, the first group meeting as soon as possible, and then decide on what topic you're gonna work on. So right now, what I'm going to do is I want to each group, okay, to select or I'm going to appoint 1 group contact for now, and then you guys can decide later on who's going to be the group contact. That's fine, okay. Now for the group 1, the first person, Maria Copper, is here. Anybody in the group 1, raise your hand. Okay, so whose name is appearing first on the list? Yours? Okay, what's your name? Is this you? Okay. All right, so you're gonna be the group contact. Congratulations. So, all right, so you're gonna that color. Let's make it red. Okay, okay. So now you're gonna gather everybody. Okay, from this is so anybody in group 1. Okay, then contact the Garima. Then she will be the she will pull the first the group meeting. All right, so now where is there? Group 2, any one? Your first one? Okay. Okay, so you're gonna be the let me get in the you have a long name. All right. Group 3. Okay, what's your name?
Last second.
Huh?
Last second. Group 3.
Oh, group 3. Last one?
No, last second.
Last 2 second? Oh, okay. So then you're gonna be. All right, so group 4. Okay, who do you want to be the? Who want to be the group contact? Okay, huh? This one?
Yeah.
This is you? Okay, you're gonna be a group contact then. Okay, group 5? Okay,
I'll be the first one.
you're the first one? Okay, then you have no choice. Okay, group 6? Anybody from? Nobody? Oh, okay. All right, which two who want to be? Okay, rock, whoever lose gonna be the group contact. Rock, paper, scissors, go. Okay, who goes? Which one? This one? Okay, it's gonna be a group contact. Okay, group 7? Come on, who is okay. What's the name? Second one? Okay. All right, so let's move on to the Zoom session. Let me need to. All right, if you're on group 8, okay, if on group 8, please like making thumbs up or give me a thumbs up on the if you're on the group 8. Who is on group 8? From Zoom session? Come on, guys, you need to volunteer. Oh. Okay, if you don't, I'll call the first name. I think this is the first. Shubham. Oh, you're here. Okay, so if you then if you don't volunteer, I will just sign for the first one. The second group, Wei Lu, okay, you are here. It's the second one. No, that's easy. I can just read the name. So the last one is Shuhas here. Oh, Shuhas. Oh, okay. All right. Good. So you want to be the. Thank you for this. Okay, you can lower your hand. Thanks. So then you will be the group contact. Okay. Now group 8. The only thing is so group 8, group 7. The two contact. If your name is on there, can you raise your hand? Make sure. I just want to make sure you guys hear me. So for the group 8, Shubham, are you here? Like, why I got no response? Okay. Liu Wei, you here? Can you raise your hand? Okay, so group 9, you got confirmed. All right. For the group 8, Shubham, you're here. If you're not here, I'm gonna change to another one. Okay. So group 8, anybody from group 8 you want to volunteer? First, I want to call the volunteer. Then, if I don't get a volunteer, then I'll call the by name. Anybody from group 8 you want to volunteer to be the group contact for now? You're the only group left. Come on. If you want to volunteer, just raise your hand. Okay. Second one, the Sindhu. Oh, okay. Vishna, you volunteer, right? Good. I see a volunteer. So, oh, that's a 9 group. So who is the group A? The group A has no volunteer right now. Come on, the group A, you guys need to volunteer someone. So yeah. So Vishna, you want to volunteer for the group A, right?
No.
Okay, let me see. Okay. Okay. Okay, so this is okay. All right, you're on the second one, you volunteer. Great. Thank you. Thank you so much. All right, so now I have let me get this first. I'll answer the question for the. Okay, so now I have everybody. Okay, so I have everybody, like each group. I mean, is with the confirmation on the. So if your name highlighted in red, you will be the group contact to gather at least for the first group meeting. Okay, then so then you guys can decide on which topic you want to work on. Like I said, this is top 5 choices. This kind of first come first serve. So I would suggest you guys can have in the that gather together as soon as possible. Now, if you don't know anybody's like an email, okay, you can then let us know. We can help you to find them. But you can find them pretty much. You should find from the directory, the website. You should be able to find them. But like in case you have trouble find their like email, okay, let us know. We can help you. So so thank you for those being the group contact, because this is a it will take some work, okay, to get everybody together. And I can tell you, sometimes it's not easy to reach everybody. And if you, in case if you have problem, let us know as well. Okay, so just I want to hopefully you guys can have the topic done for the like sometime this week. Okay, sometime this week. Then next week you guys can start to work on it. So there was a question asking, should everything including like the implementing for the MPI for Pi? Now, for if your presentation is about data analysis, okay, if it's about data analysis, you need to run some script. You should have an MPI for Pi, because you need to, if you're working with the data, I would suggest you to use MPI for Pi. Because this is the package we're talking in class. This is, I think this is the one everybody is become familiar with. If you don't want to use MPI for Pi, okay, if you want to do something else, we need to discuss about it, because I do want to make sure everybody can follow your presentation. It's then the group project is not just about finished project. It's also about like we learn from each other. Okay. So you like I'll give another. If you have a presentation, okay, you have a lot of formula and you have a lot of you spend a lot of time to dig in all details, and then you have a lot of equations. But at the end, within like 15 minutes, 60 minutes, nobody can understand you. Okay, that's also not a very good presentation, because the key is you want to say is people can learn from you. Okay, you spend time on that, people can learn from you. So in the sense that I would strongly encourage you guys to use MPI for Pi, but in case you think you can have another way to people can like making class to understand your topic better, I'm fine with it. But let's first like talk about it. Okay, I would think most of presentation should be using MPI for Pi. Okay, so any questions from the final? Yes. Strategic data set? What You mean the first person? No. Yeah. So presentation dates, after you guys choose the topic, I will assign the topic to each day. That's mainly based on that will based on like I want to group like similar topics together on one day, and then the like rest on another day. So the order is not on this is a group in order yet. Okay, but I will it will be on the based on the topics. Okay, so the dates of which group on which day is hasn't decided depending on the topics. All right, any other question? Okay, all right. So if you don't have any question, but if you're in the middle, okay, if you have any question, just let me know. Okay, shoot us an email. We will be we will get back to you. But then the one thing is important is taking top 5 choices. Okay, make sure you're sending like if you're choosing from above, make sure you send the TA 5 choices. Okay, in case the first top choice is gone, you still have other left. I mean, usually, I mean, to my surprise, in the past, usually, actually, there's not much collision. Okay, the topic collision in there. Typically, most people can get their first choice. A few of them get a second choice, but just in case we want to guys pick 5, so we don't need to go back and forth. I mean, in the very unfortunately event, like your choice for all the 5 choices be chosen, you will be then you have to discuss again. So once you have in this is you're gonna see what you're gonna see in keep an eye on the bright space, because once we having a topic has been chosen, we're gonna update it here. For example, like group 1, okay, they choosing the classroom. So then later we're gonna see then you dash, you can have in the group 1 say the classroom, okay. So for whatever if the topic has been chosen some a group before, it will be updated here, okay. Just if you see a group already been chosen, of course don't send it again. Otherwise, it's you will not get away anyway. All right, so that's about the group projects. Now next, let's talk a little bit about the penalized-based methods, okay, with the ADM implementation. Penalty-based methods is now is become more and more popular, okay, in practice. The reason is the penalization of first. Let me introduce first the penalty-based method. Then I will tell you the why it's become like more and more popular. So the goal for the penalty-based method is to impose some penalty on the complexity of the model to get lower variance. Okay, so that's sort of like the motivation. For example, for the regression, which is y equal x beta plus epsilon, right? This is what you're seeing. Very like you should be very familiar with the linear regression. So the target function, what it used to be for, we want to minimize our some SSE, right? Some of square errors. So this is error transport times error, right? The penalty-based methods, it adding actual term, okay, which is lambda plus r beta in the actual term here. This is r beta is basically a so-called penalty on the parameters, okay, penalty on the parameters. The popular r beta, the penalization item will be one is L1 norm, one is L2 squared L2 norm. Basically, this L2 norm is beta transpose beta, right? So and then the L1 norm you can see is the sum of absolute value, okay? Sum of absolute value. So for those one on the room, so this is the popular method is L1 norm, is L2 norm. So L1 is the basic summation j from 1 to p of beta j absolute value, right? L2, this is summation j from 1 to p of beta j squared. Okay, is basically is sum of the absolute value, sum of the squares. You can see they're both positive. Okay, both positive. So what it does basically is, so on one hand, your SSE, right, your sum square error, you want to minimize your target function. On the other hand, this beta also going to be increased. If beta value is too large, you're going to making this target function to be large. So essentially, okay, what this is practically the effect of this penalty term is to avoid beta become too large. Okay, beta become too large, right? So if beta is too large, say beta blow up to like infinity, then that cannot be the maximum point. Okay, so on one hand is you want to make it to be small. On the other hand, you want to make the beta, you avoid the beta not to be too big. Now, why people want to do that? Okay, why people want to do that? This is related to the so-called the variance, the bias trade-off. So if you look at the expectation of your beta hat, which is estimation, okay, minus the beta, which is true beta, this term can be written as expectation of beta hat minus expectation of beta hat plus expectation beta hat plus beta or minus beta. So what is this? Okay, beta hat is your estimation, right? It's estimation beta. Beta is your true beta. This is your true value. Okay, so typically if you having the distance between the estimation and your true value, take the square and expectation. This is called the expected error, right? This is called the expected error. This is typically a measurement how good your estimation is, right? The larger the value, the worse the estimation, right? The way you want your estimation, because you want the estimation to be close to the true value as close as possible, right? But this is because the beta hat, the estimation has a distribution, is not a fixed, has a distribution depending on the data. So therefore, we want to put the expectation on this too, right? So this is called expected error. Now, for the expected error, I can minus expectation of the beta hat plus the expectation of beta hat plus minus plus, right? It doesn't change value. This, okay, this can actually, you can see it's going to be expectation of the beta hat minus expectation of beta hat. This is going to, oh, you have a square plus, okay, expectation of beta hat minus beta square, okay. There is a cross term, okay, there's a cross term. The cross term will be 2 times expectation of beta hat minus expectation beta hat times beta hat times expectation beta hat minus beta. Okay. So there is a cross term. Now here there's a few things. Okay. This expectation is on beta hat. Okay. This is on beta hat. Inside here, this is expectation beta hat. Expectation beta hat is a fixed number, right? Beta is a true value, is a fixed number. This two you can view as a fixed number with respect to beta hat. Okay, so therefore, when you take the explanation, when you expand it, right, you group these two terms together, the second two terms together. So you have the square term on the first one. It's beta hat minus beta hat square. So this you still need to take the explanation, right? You have it. Second term here, then there's really no explanation because explanation of a constant is itself, right? So therefore, I don't have explanation up front. Instead, it's explanation beta and minus beta, right? So this term is this is called we call bias term. And you have a cross term. It's 2 times this explanation of this beta hat minus explanation beta and plus this explanation beta hat minus beta. This two things. Now this term is actually goes to 0, right? Because explanation beta hat minus explanation beta hat, then minus itself is this term go to 0. So therefore, that's why when you broke it, you only have one term. Okay, you only have these 2 items. The first term is the variance of beta hat. Right? The first term is called variance of the beta hat. Right? Because it's the expectation of beta hat minus expectation itself and takes square. So this, the first term, this is the variance beta hat. This is the definition of the variance, right? First term is variance beta hat. Second term here, this is how far away your expected estimation away from your true value. Okay, this term is called bias. Bias of beta hat. In statistics or in estimation, in history, people often focus on so-called unbiased estimation. Okay, people like for the linear regression, for the beta hat, right? The beta hat is equal to x transpose x inverse x transpose y, right? This is if you have this, we know the expectation of beta hat is equal to beta. That means your estimation expectation is equal to the true value, right? This beta hat is called unbiased estimation. So if you have unbiased estimation, then this guy can go to 0. Right, this guy goes to 0. Okay, so for unbiased estimator, the expected mean of error is the square the error is going to be equal to variance of your estimation. Okay, they are the same. So for unbiased estimator is the same. Now, like I said, for most of the thing like in the past, people focus on so-called unbiased estimator, but this unbiased estimator is it really is it better than the biased estimator? For a long time, people just assume that. Okay, people like unbiased estimator because it has a lot of the good statistical property, and the people like it. Now, later on, people actually find out. Okay, then first thing is if without this penalty term, okay, if without penalty term, if we're only solving for the minimize, this is some squared errors. This is what we get, right? We will have an unbiased estimator. If you're adding another penalty here, then this actually into the actual term into the target function. Then the beta estimation, say this beta estimation you're getting from minimize this function, the beta estimation we call it beta tilde. Okay. This beta tilde is no longer unbiased. Okay, it's become biased estimation. So biased estimation, that means this term, okay, this term is no longer 0. Okay, no longer 0. However, when we try to evaluating estimator is a good or bad, this is what we see, right? This is the expectation, this is mean square errors, right? This is called this is what we want to evaluate, because this tells us in general how far away your estimation from the true value. Okay, this is what we want. We really don't want to that's you have the bias. Now the very bias trade-off is if you can give up some of bias list. Okay, if your estimator can be a little bit biased, but if you can reduce your variance a lot. Okay, in that case, you're still going to reduce this overall errors. So in that case, it will be good. So in now see, this is our true beta. Okay, this is our true beta. And then first you having an unbiased estimator, you're gonna be like this. So let's see, this is distribution. Okay, we gave you a distribution. Let's see the one standard error. This is distribution. It will be so your beta hat is unbiased. But then it will be having a big error term around your true value, right? Compared to another estimator, okay? Beta tilde is right here. Expectation of the beta tilde is away from the true value. Okay, you have a bias. Okay, however, its variance. Okay, its variance is going to be small. It's like in general, it's just be centered around like in this small area. Overall, if you look at the error of this beta hat from away from the beta, overall it's going to have a smaller errors, right? Because it's although it's probably not on the true value, but its variance is small. Okay, it's very tight in just in this value. So therefore, the distance the distance between these two, the error term, still on average should be small. Another one is unbiased. I mean, the overall, the large number is going to be on the true value, but you have a very large variance, right? So therefore, your term is big. So in that case, if you can sacrifice a little bit bias, but if you can reduce the variance a lot, then you can overall you're going to reduce your error, estimation error. Okay, so that's the whole idea behind this is the penalty term. The penalty term basically is by sacrifice bias list can reduce the variance, making the estimation a little bit bigger. Okay, not maybe better. Maybe so that's this is how we view it. So let's stop here today. In next class we're gonna talk about like how this is like maybe the intuition behind this penalty methods, and also how do we implement this penalization using ADMM to the large data, right? We want to see is not only just good quality for small data, but we want to extend it to large data. All right, so that's it for today. I'll see you guys on Wednesday.